Topic Notes 2.1, Plate Tectonics. This is a picture of one of my favorite mountain ranges, the Grand Tetons, which is just south of Yellowstone National Park. And it's a great example of just how powerful the Earth's tectonic processes are. And we're going to learn all about it in this note set, especially because some of the most dramatic geography and mountain ranges are found underwater. So let's get started. Our main ideas for today. The Earth's crust is made up of large tectonic plates that interact with each other, continually changing the surface of the planet. And of course, be very aware of each of the targeted learning goals below. So the picture to the right was taken around 1966, and it's one of the first full disk pictures of the Earth we've ever had. And this is really important because the perspective that people got when they got to see the planet from a distance was huge, and really still is. In 1969, the Apollo 8 crew took this picture on the right, called Earthrise, which shows just how small the Earth is, even from our own moon. Now, we've even gotten further pictures away nowadays from the planets and even beyond the solar system, where the Earth is just a little speck. And this is really important because everything in human existence has all occurred on this one blue marble. And it is our home, and the systems that work it, both geologically and biologically, support life as we know it. And that's why it's so important to understand how this planet functions. And that's our really goal here in this couple of note sets. Now, the title of our notes today is Plate Tectonics. Now, the Greek word tecton is a noun meaning builder or carpenter, and this applies very well because the Earth is constantly rebuilding itself. This is a modern picture of the Earth, nice in color and satellite view, but if you were to go back 100 million years ago, it would look different, and that's the whole point. The Earth is constantly changing. Now, these changes did not go unnoticed. In 1912, the German scientist Alfred Wegener proposed the theory of continental drift. Now, continental drift is a theory supporting the possibility that the continents are able to move over the Earth's surface over time. Now, Wegener did not just come up with this on a whim. He looked at evidence from around the world. Now, one of the first lines of evidence you probably have been exposed to is the puzzle-like fit of the continents. Now, if you take Africa and South America, they fit together pretty well, and Wegener saw that. But he also saw similarities in other continents as well. And that really got him thinking, but there was more to be found. Fossil evidence was also really huge. The distribution of specific fossils across continents really gave a good idea. For example, there was the Mesosaur fossil, which is kind of a freshwater reptile that was found in both the southern tip of South America and Africa. Now, today, that's separated by a huge ocean. They would never have been found together, but there they are, same exact fossils. Also, you have plants that exist in the Arctic and as fossilized forms that are tropical plants. So this gives us a lot of evidence. Now, certain geologic structures tend to form together. If you actually go back and look at the Appalachian Mountains, they were formed essentially along with the same mountains you'll see in the British Isles, the Scottish Highlands, things like that, the Caledonian Mountains. This was also evidence. You have various different geologic features and rock formations that were similar between the continents that were probably formed together a long time ago. So this came to the idea of Pangaea, all of these continents being together at one point in time, a supercontinent that formed over 300 million years ago from all the land masses of Earth and began to break apart around 250 million years ago. Now, Alfred Wegener did not have a clear mechanism as to how this happened, and generally other scientists and the general public looked at this hypothesis and was like, this could not happen. These are huge, massive tectonic plates. They can't be just drifting around. But it took until the 1960s before evidence started to support Wegener's ideas, and a revised theory was formed, you know it, as plate tectonics. So what was this new evidence? So this comes back to the influence of World War II and mapping the ocean floor. So the military needed a way to detect enemy submarines in the ocean, and so sonar was developed, which is sound navigation and ranging, and that was a huge benefit to the oceanographic community. So essentially what they were doing is using sound, pulsing it out, and that sound would come back to the ship and it would give them a reading of how deep the water was. And so we started collecting that data all over the place. Now, there were some important pioneers in this work, including Mary Tharp and Bruce Hazine, who used data from the various ships to map the North Atlantic and essentially discovered the MidOcean Ridge. And this was really unique, especially considering Mary Tharp, who was a female geologist, and she was the first to actually start to note the Mid-Atlantic Ridge in the data. And at the time, she wasn't even allowed as a woman to go out on the ships. Now, by 1956, they started to correlate some of the earthquake data with the Mid-Ocean Ridge, and Maria Tharp started to realize that Alfred Wagner's old ideas of continental drift actually lined up with the evidence she was finding on the ocean floor. And this was pretty huge. And in 1977, Mary Tharp and Bruce Hazine published the world ocean floor map that you see here today. In many ways, seeing the Earth like this with the topography filled in for the ocean was just as big of a revelation as seeing the Earth from space. These different perspectives really gave scientists the ability to see the Earth in a way that we had never looked at it before. And it really broke a lot of barriers in terms of how we understood the functioning of our planet. Now, Harry Hess was a U.S. Navy officer who served over in the Pacific Ocean. And as he was on his missions, he would often, of course, collect the sonar data from the ocean floor. That helped add to our knowledge about the ocean floor in the Pacific specifically. But he also, in 1962, published a book called The History of Ocean Basins, which essentially laid out the concept of seafloor spreading, which was the landmark mechanism that supported what Alfred Wagner was seeing with all his other evidence, and eventually, again, provided the framework of our modern theory of plate tectonics. This is also a great way to highlight how theories can change over time when new information, especially with new technology, comes into play that redefines what we think we know. And essentially, what the deal is Alfred Wagner wasn't wrong. He just didn't have the ability to know about the ocean floor, and thus he didn't have the ability to really make the kind of conclusions that Harry Hess did, for example. So let's go ahead and move on and see what else we've learned. Now, we actually know a decent amount about the interior of the Earth, but how we know it is kind of interesting. Scientists use earthquakes that produce seismic waves to deduce the density of Earth's interior. So let's just define earthquakes for a moment. An earthquake is a sudden release of energy inside the Earth that creates seismic waves, usually caused by the movement of tectonic plates or volcanic activity. Now, these seismic waves move through different densities at different speeds. So essentially, if we know what the epicenter of or where the earthquake occurred, we can then measure the waves where they arrive in different parts of the planet, and that gives us essentially an ultrasound of the Earth to determine what the consistency of various different layers are. Now, this has essentially allowed us to understand the layers of the Earth. So at the very center, we have what we call the core, which is this dense central region within the Earth. Now, dense elements, mostly iron and nickel, tend to be there, and it's made up of a solid inner and a liquid outer core. Next up is the mantle, which is a region of semi-solid molten rock within the interior of the Earth between the core and the crust, and it's capable of very slow movement over geologic timeframes. Now, you can also break the mantle up into some parts, and we're going to talk about the asthenosphere, which is the nearly liquid layer made up of the uppermost part of the mantle. Now, above that, you essentially have the crust, which is the outermost layer of rock on the Earth. Now, we have two different components of that. We have oceanic crust, which is the dense basaltic layer of crust that makes up the bottom of the ocean basins, and then the continental crust, which is the thicker, less dense crust that makes up the foundation of the continents. We also call the outermost layer of the Earth's crust the lithosphere. Now we have enough knowledge to put together the theory of plate tectonics. So plate tectonics is the process where large sections of Earth's crust are in constant movement over the fluid mantle, causing earthquakes and volcanoes at the borders between plates. And so you can see in this diagram all of the major plates on the Earth. We've got the Pacific Plate, which is very huge, the North American Plate, then the smaller ones like the Caribbean Plate and the Nazca Plate. These massive plates are constantly interacting with each other, grinding past one another, sliding under each other, pushing against each other, essentially making the ever-changing planet we see today. So let's look at some details. These lithospheric plates essentially move or float independently on the asthenosphere. Continents are embedded in these lithospheric plates, along with ocean basins. This is where Wagner couldn't really get that information at the time. He was thinking they were floating around independently, but they're really not. Continents are part of a larger plate. Now, these plate interactions cause mountain ranges, mid-ocean ridges, and deep trenches that are all important to marine science itself. And again, Wagner really couldn't have known some of this stuff at the time, but his evidence was still spot on. Now, the MidOcean Ridge is a mountain range with a central valley on the ocean floor at the boundary between two what we call divergent tectonic plates, where new crust forms from upwelling magma, and the plates are essentially moving apart. A great example of this, and one of the only examples that it actually comes up on land, is in Iceland, which is kind of neat. Most of it is all underwater. So let's start looking at some of the modern evidence for plate tectonics, and we'll start with seafloor spreading, and specifically magnetic polarity reversal. Now, basaltic rocks commonly found along the seabed are igneous rocks, and they're essentially formed from cooling molten magma. Now, basalt naturally has iron material called magnetite within it. Now, this aligns to the Earth's magnetic field at the time of its formation, so the north-south magnetic pole scenario. Now, the pictures on the bottom right are some of that basalt. Now, as lava comes out on the seafloor, it sort of forms these pillow-like shapes, which are kind of interesting. They're actually called pillow lava. Now, one thing to note here is that Earth's magnetic poles, north and south, have not always been the way they are. In fact, they flip back and forth, and it's a bit of a mystery for science, but we'll get back to that in a minute. Now, let's look back at that seafloor. We have what we call paleomagnetic stripes, which is the pattern of magnetic stripes on the ocean floor due to the reversals in Earth's magnetic field and seafloor spreading. So essentially, new seafloor comes and forms at the MidOcean Ridge. That new seafloor is aligned to the current magnetic field of the Earth. As the new molten rock hardens and ages, it starts to be pushed away from the center of spread. And then the new rock that comes out is going to solidify and align to whatever new magnetic field happens to be going on Earth at the time. Let's also take another step back and define polarity. Essentially, polarity is having two opposite states of being on either end, such as the north and south pole or positive and negative end of a magnet. So essentially, think of flipping a magnet, north-south ends of a magnet, back and forth, back and forth. Every time you do so, the new seafloor that's formed in that new alignment is going to form according to the current magnetic alignment and field. Now, this banding pattern that we see moving away from the ridge correlates with Earth's reversals in its magnetic field, which happen on average about every 250,000 years. Oddly enough, we still don't fully understand why it happens, and there's kind of a lot of science behind it that we're still working out. It's very interesting stuff. Big takeaway here is that the magnetic polarity reversal and paleomagnetic stripes is a big piece of the evidence for seafloor spreading and plate tectonics. Now, another important line of evidence has to do with the age of the seafloor. Now, the rocks on the seafloor near the mid-ocean ridges are younger than that of the continents or farther away from the ridges in general. And you can see that in this diagram where the kind of red right along the ridges is the youngest rock. Then you go out into the cooler colors, they're going to be older and older. Now, we do this through carbon dating and looking at isotopes and things like that, so it's pretty accurate. And it really gives you that sense that that's where the new seafloor is forming, and then the old seafloor is farther away as it's being pushed away from the spreading center. So you get it. There's evidence stating that these large lithospheric plates are moving, right? Well, how do these massive plates that literally defy human comprehension in terms of how big and heavy and large they are, how are they moving? So the first thing we're going to look at is what we call mantle convection. And that's where heat from the Earth's core is transferred through the mantle, through what we call density currents, moving the plates along the convection current. Now, you see this in a pot of boiling water, right? When you start to heat the water, it rises to the surface and then it circulates back down along the sides until everything becomes really hot. This is essentially what's happening in the mantle. Now, remember, we mentioned the mantle is semi-liquid. It's kind of dense. It's not like a liquid that we think of in like a cup of water, but it's very thick and viscous. And so that heated material moves up and then it slides along the bottom of those large lithospheric plates, creating that friction. And that's what starts to move those plates ever so slowly. And you can see on the right, there's essentially a simulation by a scientist at the University of California that sort of put this into the computer and sort of had it give you that sort of outfall. And you can see where the MidOcean Ridge would be as that red plume is coming up. And then the red and orange sort of is the movement away from the ridge. And the bluer areas are areas of sinking convection. And this temperature is really about density, right? The hotter that temperature, that red area is much less dense than the cooler areas, which are more dense. Now, there are a couple of other mechanisms that are probably related to the convection that we use and talk about. One is called ridge push, which is a force that is exerted by cooling, subsiding rock on the spreading lithospheric plate at the MidOcean Ridge. So essentially, that's that rock piling up and pushing down. And then the slab pull, which is a force at the subduction boundary that the sinking edge of the subduction plate exerts on the rest of the plate, essentially sucking it under. Now, these lithospheric plates are very large and very heavy. So this mantle convection and ridge push and slab pull, all of this stuff happens very slowly. The plates only move about 2 to 5 centimeters a year. So it takes quite a long time, but you fast forward 100 million years, 200 million years, and you see a huge difference in the planet. The last thing we're going to look at are plate boundaries. Now, plate boundaries are characterized based on their interactions, and this graphic essentially shows you the location of the majority of earthquakes and volcanoes around the world, and you should probably already note this looks a little similar as the lines that I showed you when I showed you all of the different plate boundaries. Plate boundaries are where a lot of geologic activity is happening. First up are the convergent boundaries. Now, convergent boundary is when two or more tectonic plates come together. Now, when you have two lithospheric plates coming together, you might have a variety of either a lithospheric plate with an oceanic crust or a continental crust or some combination thereof. Now, when you have an ocean crust and a continental crust converging together, or an ocean and an ocean crust converging together, one of those plates is going to subduct or go underneath the other. It's usually the denser of the two, which tends to be the oceanic plate or anoceanic plate. This essentially causes what we call a trench, which is a narrow, deep depression on the ocean floor with relatively steep sides. And these trenches are the deepest parts of the ocean. Now, not only do you find trenches near convergent boundaries, but you also find volcanoes. Volcanic activity occurs right along those borders, and we're going to talk a little bit about that in another lecture. And also mountain chains. If you know the Himalayan mountains, we actually have two continental crusts coming together there, and thus that's forming a massive mountain range. Next, we have divergent boundaries. This is where two tectonic plates are moving away from each other, and we've talked actually about this quite a lot because they're mid-ocean ridges. They're constructive zones that produce these mid-ocean ridges with new ocean floor being formed. And finally, we have transform boundaries. This is when two plates are moving anti-parallel directions, creating friction between them. They're sliding past each other. Great example of this is the San Andreas Fault in California. Essentially, when you have increased friction, it causes cracks called faults to form. And then built up pressure along faults can cause earthquakes and even tsunamis, which again is something we're going to get into a little bit more on another lecture. All right, that was a lot of information and a lot about how our planet works. So let's just go over that main idea one more time. The Earth's crust is made up of large tectonic plates that interact with each other and continually change the surface of the planet. All right, until next time, keep learning.